My name is Haley and I'm a second year bio major, and today we're going to be helping you solve problem number 8 from chapter 6.1 in the general chemistry workbook. I'd advise that after you see the problem, you try it on your own and then wait for us if you still can't figure it out. So before we start actually plugging stuff in and solving this problem, we should take a minute and talk about what it's actually asking us. The problem gives you a wavelength of microwaves and asks for how many photons are emitted per second. We know we can solve for the energy of one photon using Planck's equation, which gives us the energy of one photon of light based on its frequency, and it can be written as energy is equal to hv, where h is Planck's constant and v is the frequency of light. We also need to determine the frequency of the wave, and for that we use the wave equation, which states the frequency of the light is equal to the speed of light times the wavelength, where c is the speed of light and that's the wavelength. So c is a constant and it is equal to 3 times 10 to the 8 meters per second, and that's true for all electromagnetic waves. And h, which is Planck's constant, is equal to 6.26 times 10 to the negative 34 joules per second. When we substitute these two equations together, we get our final desired equation, which is E equals hc over lambda. Now we just need to plug in the numbers given in the equation to solve for the energy of one photon. So first I'll write the equation that we used on the previous page, E equals h times c over wavelength. And we're going to need to solve for the energy of one photon, and in part A, the wavelength is equal to 12.2 centimeters. So wavelength equals 12.2 centimeters, which is also 0.122 meters. So when we plug in Planck's constant, which is 6.626 times 10 to the negative 34 times the speed of light, all divided by 0.122 meters, we get a final energy of 1.629 times 10 to the negative 24 joules per photon. The problem also states that we're dealing with a 1000 watt microwave, and 1 watt is equal to 1 joule per second. So now we can say that one photon emits 1.629 times 10 to the negative 24 joules, and if we multiply that by 1000 joules emitted per second in the microwave, our units will cancel out and we'll get photons per second, and here we get 6.13 times 10 to the 26 photons per second, which is our final answer for part A. Part B is pretty much the same problem, except now they ask us to find it if we have a 15 centimeter wavelength as opposed to 12 centimeters like the previous problem. So we're going to do the same thing. We're going to say E equals hc over wavelength and plug in all of our numbers. It's Planck's constant times speed of light divided by 0.15 meters, and we get energy per photon is equal to 1.325 times 10 to the negative 24 joules per photon. And we'll do the same thing as before. One photon emits 1.325 times 10 to the negative 24 joules. In the 1000 watt microwave oven, so 1000 joules times 1 second, and that gives us 7.54 times 10 to the 26th photons per second. And that is the end of part B.
Hi, my name is Julian. I'm a third year ME, and I'm going to be walking you through part C of this problem. So part C asks how many photons are necessary to raise the temperature of this amount of water. So first off, we have to find the energy in one photon at a certain wavelength, and we're going to be using the wavelength from part B of 15 centimeters. So the equation for energy of one photon is E, energy in joules per photon, is equal to hc over the wavelength. So h and c are constants, where h is Planck's constant, which is 6.626 times 10 to the negative 34 joule seconds. C is the speed of light, which is 2.998 times 10 to the 8th meters per second. And then our wavelength, we want in meters to cancel out with the other meters. So for the wavelength of 15 centimeters, we convert that, 0.15 meters, and we plug it into our E equation. So H is in joule seconds, times C, which is meters per second, over our 0.15 meters. So we can see here that the meters will cancel, these seconds will cancel, and we're going to be left with a value of 1.324 times 10 to the negative 24th joules. And this is for one photon. So that's the first part of this problem. So next we have to calculate the amount of energy required to raise 350 milliliters of water from 20 degrees Celsius to 95 degrees Celsius. So the equation for that is Q equals mc delta T. So m is our mass of water, and we know that 1 milliliter of water weighs 1 gram. So our 350 milliliters are going to weigh 350 grams. Next, C is the specific heat of water. So C for H2O is 4.186 joules per grams degrees Celsius. And our delta T is equal to temperature final minus temperature initial. This can either be in Kelvin or in Celsius because it's a change in temperature, so it doesn't matter what you choose. So that's going to be equal to 75 degrees Celsius. So if we plug in all these values, Q, which is in joules, is going to equal 350 grams times 4.186 joules per gram degrees Celsius times 75 degrees Celsius. So our degrees Celsius are going to cancel, and our grams are going to cancel, and we're going to be left with Q is equal to 109,883 joules. So now that we have E and Q, recall E is 1.324 times 10 to the negative 24th joules per photon. And our Q is 109,883 joules. So the question asks for how many photons are necessary, and we can see from dimensional analysis that dividing Q by E is going to cancel out the joules and give us the number of photons. So if we take 109,883 joules and multiply that by one photon over 1.324 times 10 to the negative 24 joules. Our joules will cancel. We're going to be left with our answer, which is equal to 8.297 times 10 to the 28th photons. Thank you.